Hello, my name is Joshua Levin Kurniawan. I'm a final year aerospace engineering student from ITB. And today I'm excited to introduce you about our latest project, the Aircraft Stability Analyzer app, developed in collaboration with Mr. Yasdi. And this innovative app built using MATLAB, and it is designed to revolutionize the way we analyze aircraft, especially in preliminary design phase. This app enables users to interactively analyze the dynamics and stability of an aircraft. It offers four main functions: static and stability analysis, trim triangle analysis, aircraft model trimming using a Simulink model, and a flight mode analysis using pulse obtained from the linearized equation of motion. Let's delve into the workflow of our Aircraft Stability Analyzer app. Firstly, users input aerodynamics data for their aircraft, and this can be done in various ways. The first one is entering first-order derivative aerodynamics data from software or wind tunnel testing. The second one is uploading a .out file from DATCOM software. Or the third one is selecting presets from the app, which include popular aircraft models like Cessna 747 and more. Once the data is in, users can analyze the trim triangle of the aircraft. This feature allows for the estimation of steady-state symmetric flight condition of the aircraft, factoring in elevator deflection and angle of attack. Trim triangle analysis is important for assessing the current CG or center of gravity movement or determining the allowable or designed CG location for a new aircraft design. Next, the program can trim the aircraft for steady, symmetric level flight using the known cruise airspeed or angle of attack, considering the specified atmospheric conditions. This allows the users to trim the aircraft around a defined fixed point, obtaining the aircraft state space. With this state space model, users can delve into the dynamic stability analysis, observing the aircraft dynamics over the time. Moving on, the app enables the users to examine whether the aircraft meets static stability criteria or not. This assessment helps determine how the aircraft responds to disturbance, whether it amplifies or opposes them. Let's take a closer look to the app interface, starting with the aerodynamics tab. Here, the users can input the aerodynamics derivative data of the aircraft. First step is to choose the source of aerodynamics parameters. Users have three options: manual input, uploading a .com.out file, or using the provided presets. If the users choose for manual input, then they can input the aerodynamics derivative data. Currently, the app only supports first derivative input for aerodynamics. However, this app providing flexibility to enhance the model fidelity using Simulink, which we will discuss later. Following this, users can input the atmospheric model for the aircraft operations. The app assists in automatically calculating air density and pressure using ISA model. Next, users can input geometric parameters and control surface aerodynamics coefficient. Once all parameters are entered, clicking Setup Parameters and save the current aerodynamics properties. Now, let's explore the Static Stability tab. This section simplifies the process by allowing the users to input the cruise Mach number and then clicking Analyze to generate results. On the right-hand side, users can find a comparison chart showing the typical value for pitching moment derivative and yawing moment derivative based on Raymer's data. The analysis results are displayed in a static stability coefficient table, where the sign value indicates the static stability of the aircraft. A green indication signifies the static stability, while the red indicates instability. Moving on to the Trim Triangle tab, users can set aircraft properties such as weight and operating airspeed. they have the flexibility to choose between analyzing the trim triangle in gliding mode or powered mode. Toggling the engine settings, users can switch between gliding mode and powered modes. If the engine settings is activated, users must input engine parameters, including the vertical distance between the CG and engine or ZT and the thrust incidence angle or IP. Next, users input the available and chosen CG location. Upon completing these inputs, clicking the Analyze will generate the trim triangle result. The trim triangle graph is then displayed on the right-hand side of the application interface. Let's explore to the next step, where the users can automatically generate a simulating model of the aircraft and finding its steady symmetric level flight condition. Firstly, users need to ensure that the aircraft properties are complete. By default, these properties are automatically filled when the users is already completed the trim triangle tab. To initiate the process, users click Analyze, which create a user aircraft object variable in MATLAB workspace. Next, users select the known condition, either it is cruise speed or angle of attack, to trim the model for steady symmetric level flight. Clicking the trim model automatically generates a simulating model of the aircraft. For the user seeking to enhance the model fidelity for further analysis, they can directly modify the simulating model and then retrim it by pressing trim model again. It is important to make sure that Sim6 DOF simulating file is located on the current directory path. Finally, users can produce the linearized model of the aircraft by simply clicking the linearized model. In the linearized equation of motion tab, users can generate the A and B matrices of state space model by clicking the Generate Linear Model button. The app utilized the general notation for state space, where the first derivative of the state is equal to the matrix A multiplied by the state vector x plus matrix B multiplied by input vector u. The app will automatically decouples the 6 degree of freedom linear model into longitudinal and lateral directional modes. For the longitudinal mode, the state vector consists of u body axis forward speed, w body axis downward speed, q or pitch rate, and theta, that is the pitch angle. For the lateral directional mode, the state vector comprises of v body axis rightward velocity, p roll rate, r or yaw rate, and phi or roll angle. The users also can view the matrices and eigenvalues for each mode, providing valuable insights to the dynamic behavior of the aircraft in both longitudinal and lateral directional motion. In the Dynamic Stability tab, users can assess each mode of flight using the linearized model, but currently, the app only supports for conventional aircraft only for this tab. In the longitudinal mode, users can analyze the phugoid mode and short period mode. The phugoid mode typically consists of two pairs of imaginary poles, while the short period mode comprises one pair of imaginary poles with two real poles. In the lateral directional mode, users can evaluate the Dutch roll, spiral mode, and roll subsidence mode. This type enables the users to assess handling qualities by analyzing damping ratios and halving or doubling times of the poles. That's all from me. If you have any further questions, suggestions, or update requests, feel free to reach out to me via email or comment on the post below. Thank you.